You already know that scaling inference-time compute is basically the new driver of large language model performance, right?
Oh, absolutely. I mean, it's the whole ball game right now.
Yeah, but what if I told you that inside your GPU right now, your cutting-edge sub-quadratic models are they're literally starving.
Starving is honestly the perfect word for it.
Right. Because you look at a performance profiler during like autoregressive decoding, and the compute cores are practically asleep. Meanwhile, the memory bandwidth is just completely redlined. It's this severe diagnostic imbalance.
Yeah, it is the absolute definition of a hardware bottleneck. We're talking about a critical starvation of the arithmetic logic units. And to make matters worse, historically, the linear models that attempted to fix this memory-bound nature, they kind of traded away fundamental capabilities just to achieve their theoretical algorithmic efficiency.
Right, which perfectly brings us to our mission for this deep dive. Today we are dissecting the source paper Mamba-3, Improved Sequence Modeling Using State Space Principles.
It's a fantastic paper.
It really is. And the authors here took a strictly inference-first perspective. They completely overhauled the state space model, or SSM design, without blowing up the parameter counts. Because, I mean, if you're building or deploying models, you know the industry standard transformers are fundamentally bottlenecked.
Yeah, by the linearly increasing memory demands of the KV cache.
Exactly. The KV cache and, of course, their quadratic compute requirements.
And that quadratic scaling is precisely why the field has so aggressively pursued sub-quadratic architectures. Models with constant memory and linear compute footprints, like Mamba-2 and gated DeltaNet.
Right.
But as you mentioned, their theoretical elegance, it didn't always translate to actual silicon utilization. And surprisingly, they actually failed at some really basic state tracking logic.
Yeah, which is wild. But the Mamba-3 architecture introduces 3 core methodological leaps to fix this. It essentially pushes the Pareto frontier of both inference efficiency and model capability. But to understand how they fix the model's logic and hardware utilization, we first have to look at how they fixed its fundamental perception of time.
Because time is continuous, but tokens are discrete.
Exactly. Continuous time state space models must be discretized for sequence modeling, but the prior methods were, well, mathematically lacking. Okay, let's unpack this, the discretization problem.
Yeah, so in earlier iterations, specifically Mamba-1 and Mamba-2, the authors relied on a heuristic approach called exponential Euler discretization.
Right.
And assuming you're familiar with basic numerical integration, the Euler method is just a first-order approximation.
It's like calculating the area under a curve using flat rectangles. Right?
Wow.
You anchor to one side of the time interval and just assume the state input derivative remains perfectly constant across that entire time step.
Exactly, it's flat. And it functions fine as a baseline, but in the context of highly complex, high-frequency sequence modeling, it is inherently lossy.
It leaves a ton of signal on the table.
It really does.
But Mamba-3 introduces exponential trapezoidal discretization. So instead of that flat first-order approximation, it's more like using slanted roofs. It uses a data-dependent convex combination of both interval endpoints, so it tracks the actual continuous curve of the data much, much more closely.
And the mathematical implications of shifting to that generalized trapezoidal rule are profound for state space models. You immediately achieve a second-order accurate approximation of the state input integral.
Oh, wow.
Yeah, if we evaluate the local truncation error under standard stability assumptions, the error rate actually scales as $1.
Which is a massive improvement.
Huge. It's a massive improvement in mathematical precision over the error bound of the old Euler method. It allows the neural network to capture far more expressive continuous time dynamics within that discrete tokenized framework.
Okay, so I hear the error bounds, and, tightening up an integral approximation makes perfect sense mathematically. But I am genuinely puzzled by how this translates to the code.
How so?
Well, tightening a mathematical bound doesn't usually change the actual neural network topology, right?
Yeah.
Like, what does this trapezoidal shift actually do to the network architecture in practice?
Okay. It fundamentally alters the core recurrence mechanism itself.
Really?
Yeah, when you mathematically expand this new exponential trapezoidal recurrence, something highly unexpected naturally emerges from the equation. Because the update for the hidden state, H now relies on a convex combination of the current input $6 and the previous input $6. The math inherently forms an implicit convolution of size 2.
Wait. So
Oh.
just by changing the discretization formula, a causal convolution naturally materializes inside the core recurrence loop.
That is the beauty of it. It is applied directly on the state input, which is that by-do xt del term. In standard state space models, you materialize your state input, and then you just run your linear recurrence. But here, because of that convex combination of the endpoints, you're effectively applying a with-2 convolution weighted by your discrete beta and gamma step parameters before the data even passes into the linear recurrence matrix.
That is incredibly elegant. And the paper notes that Mamba-3 combines this mathematically implicit convolution with new, explicit, learnable Bido and $6 bias terms, right?
Yes, exactly.
And these biases introduce data-independent components into the SSM that function similarly to structural convolutions.
Yeah.
So because of this combination, Mamba-3 can just completely rip out the external short causal convolution layer.
Which is wild because that layer was universally standard. It was considered strictly necessary in Mamba-2 and gated DeltaNet.
Right.
But by letting the mathematical discretization do the heavy lifting, they streamlined the entire block architecture. They basically removed an architectural hack just by fixing the underlying math.
That's so satisfying. But fixing the time update is really only half the battle here. Because even with perfect discretization and a cleaner block architecture, previous linear models were fundamentally, I guess, blind to certain types of algorithmic logic.
Yes, due to the nature of their state matrix.
Exactly. If we look at the state matrix, there is a massive expressivity gap. In models like Mamba-2, the state transition matrix restricts its eigenvalues strictly to real numbers.
A major theoretical limitation that has plagued real-valued state space models since their inception, honestly.
Right. And what that means is the hidden state completely lacks any rotational dynamics. Like, it can scale an input up, it can decay an input down to 0, but it cannot rotate an input in the hidden space.
It's stuck on a line.
It's stuck. And because of that, it fails completely at solvable group regime tasks.
The TC0 task.
Yeah, exactly. TC0 task. A classic example is the parity task, literally just determining if a sequence of bits contains an odd or even number of ones. A simple, basic one-layer LSTM can solve this easily, but real-valued SSMs fundamentally cannot.
What's fascinating here is how we solve that expressivity gap. Complex-valued SSMs. By allowing the eigenvalues to be complex numbers, the hidden state can subtly represent those rotational dynamics. Think of complex numbers rotating around a 2D plane.
Right, the phase shift.
Exactly. Mathematically, a parity function on binary inputs can be solved by an update rule that applies a 2D rotation matrix by y radians based on the input. You simply cannot express that specific geometric rotation with strictly real eigenvalues.
But, and this is a big but, there is a massive efficiency trap here for anyone trying to train these models. Historically, deep learning architectures have experimented with complex numbers, right?
Oh, yeah. Early linear time-invariant models like H3 or RetNet played with them.
And they generally degraded standard language modeling performance. Plus, computing complex numbers inherently doubles your memory footprint and compute overhead. I mean, if you are deploying this in production, you do not want to double your VRAM requirements. So how does Mamba-3 bypass this trap while keeping that rotational expressivity?
So the authors rely on a brilliant mathematical equivalence. It's detailed in propositions 2 and 3 of the source paper. They provide a rigorous proof that you can take a complex valued state space model of state size 2R2 and perfectly map it to a real valued state space model of state size $.
So you're taking a non-dimensional complex state and perfectly mapping it into a non-dimensional real state. Can you break down the mechanics of that mapping?
Yeah, so you construct a block diagonal transition matrix composed entirely of 2x2 data-dependent rotation matrices. Instead of tracking a single complex number with a real and an imaginary part, you track 2 real numbers, and you apply a 2x2 rotation matrix to them at each time step.
Okay, I'm following.
And under the exponential Euler, or that new trapezoidal discretization we just discussed, applying this block diagonal matrix of rotations to a real system is mathematically identical to running the complex system.
Wow. But computing a block diagonal matrix of rotations recurrently across thousands of tokens, that still sounds computationally heavy for a custom CED kernel, doesn't it?
Well, if we connect this to the bigger picture, the authors realized that unrolling this block diagonal rotation across sequential time steps is mathematically identical to something the industry has already highly optimized.
Which is?
Applying a data-dependent rotary positional embedding.
The rope-y trick.
The rope-y trick.
Okay, that makes perfect sense, because if you have a complex eigenvalue, multiplying by it repeatedly over time shifts the phase, which rotates the vector. And applying a rotation proportional to the time step 2 is the exact mathematical definition of a rotary positional embedding.
Precisely. In the state-space duality framework, the $1 and $dollar components act functionally as your keys and queries. So you apply these data-dependent rope-E rotations directly to the $1 and $dollar vectors.
That is so clever.
It really is. You gain all the state tracking power and rotational dynamics of a complex valued ODE, but you implement it using the highly optimized, real-valued row kernels that hardware accelerators already process with incredible efficiency.
That is an absolute masterclass in algorithmic translation. And the empirical data proves it works, right? Because when the authors tested this on formal language tasks, Mamba-2 hit roughly 1% accuracy on parity and modular arithmetic. Basically, it was random guessing. It just physically cannot learn the operation.
And Mamba-3?
Mamba-3 hits near 100%.
Wow!
Yeah. It solves the state tracking deficiency entirely just by tricking the real-valued matrix into behaving like a complex one using row B.
It perfectly demonstrates the value of addressing algorithmic bottlenecks through rigorous mathematical translation, rather than just brute forcing the problem by scaling up the parameter count.
Absolutely.
Yeah.
Which brings us to the actual hardware utilization. Because, okay, we now have a mathematically rigorous, highly expressive state. But none of that matters if the GPU is still sitting idle during token generation.
Right. We return to that memory-bound decoding problem we established at the beginning.
Here's where it gets really interesting. Let's talk about arithmetic intensity. For those tracking performance metrics, arithmetic intensity is the ratio of floating point operations FLOPs to memory traffic.
Ops per byte.
Exactly. Imagine a high-speed factory. Those are your tensor cores waiting on an incredibly slow single-lane conveyor belt, which is your memory bandwidth. During the decoding phase, generating one token at a time, state space models are entirely memory-bound.
Completely.
They have to pull the massive hidden state from high-bandwidth memory into the FRAM, perform a tiny amount of math, and then write it back. Mamba-2 has an arithmetic intensity of about 2.5 operations per byte.
2.5. And just to ground that number for you, an NVIDIA H100 GPU, utilizing bfloat16 tensor cores, has a theoretical maximum throughput of roughly 295 operations per byte.
2.5 operations versus a capacity of 295.
It's staggering.
The GPU is literally starving for math. The conveyor belt is crawling, and the factory workers are standing around doing nothing.
So, to solve this starvation, Mamba-3 transitions from a single output, or CISO sequence dynamic, to a multi-input, multi-output, or MIMO architecture.
Okay, walk us through that architectural shift. How does moving to MIMO artificially inflate the math to feed those tensor cores?
Right. So in a standard CISO Mamba model, the core state update calculation involves taking an outer product between the input vector $6 and the projection vector $.
Yeah.
If your hidden state size is nonular and your head dimension is dollars, you're basically executing a low-intensity outer product that only yields FLOPs proportional to 9LR times TAC.
Which is very little math.
Very little. But in the MIMO formulation, we expand both the input $6 and the projection $$ by an extra rank dimension. Let's call it 2. So instead of 1D vectors, $6 becomes a matrix of shape, and $$ becomes a matrix of shape no-nuller.
Oh, so that low-intensity outer product is mathematically transformed into a true matrix multiplication.
Exactly. It becomes an anular matrix multiplied by a nuller matrix. You are now feeding dense matrix multiplications to the tensor cores.
Which they love.
They love it. And the memory traffic, which is still entirely dominated by loading that massive non-dimensional hidden state matrix that doesn't significantly increase because the rank $3 is kept very small, typically something like Wimmer of 2.0.
Got it.
But the computational FLOP is increased by a factor of $3. You artificially inflate the mathematical workload to soak up the idle compute cycles while the system is waiting on memory fetches.
Okay, but I'm going to play devil's advocate here. I am genuinely skeptical. If you inflate the mathematical FLOPs by a factor of 4 just to keep the tensor cores busy during humans decoding, wouldn't that absolutely nuke your training time?
That's a fair question.
Because during the training phase, when you were processing thousands of tokens in parallel, you were compute-bound, not memory-bound. So multiplying your training compute by 4 sounds like an incredibly expensive trade-off.
And that is the exact trap you'd expect to fall into, honestly. It's why MIMO approaches haven't been widely adopted until now. But the authors bypass this training bottleneck using a highly specialized, chunked algorithm workaround, and it's deeply integrated with the state-space duality parallel scan.
Okay, how does the chunking offset the math?
So during training, modern state-space models divide the long sequence into manageable chunks. Within a single chunk, they run a parallel quadratic matrix multiplication.
Right, the interchunk work.
Exactly. And then across the chunks, they run a linear recurrence. The key insight for MIMO is shrinking that chunk size. If they set the MIMO chunk size to exactly $1, the standard CISO chunk size, the all-taller intra-chunk work drastically decreases.
Oh, I see.
Yeah, it decreases enough to perfectly offset the fact that the matrices are now 5 times larger.
So the FLOP count inside the chunk remains identical.
Correct. Now, you do have $3 times as many chunks to process sequentially, so the inter-chunk recurrence workload does increase. But the net mathematical result is that the total training overhead scales, at worst, linearly by dollars rather than quadratically.
That is brilliant. And for anyone writing custom Triton kernels, because the compute latency of the inter-chunk recurrence can be heavily parallelized and overlapped with memory movement, a MIMO rank of 4 only incurs about a 2x slowdown in actual training wall clock time, not 4x.
It is hardware-aware algorithm design at its absolute finest. You accept a very manageable linear slowdown during training, and in exchange, you get 4x the computational expressivity during inference with virtually 0 increase in decode latency. You are simply utilizing the compute cycles you were previously wasting.
Incredible. So we have the theory, we have the exponential trapezoidal discretization fixing the time update, we have the rope E trick solving the complex state expressivity gap, and we have the MIMO architecture artificially inflating arithmetic intensity.
It's quite the trifecta.
It really is.
Yeah.
But theory is useless if the model doesn't actually predict the next token better. Let's look at the hard data. The authors validated this by training models at various scales, up to 1.5 billion parameters, on 100 billion tokens of the fine Webedu dataset.
This raises an important question. How much does Mamba-3 actually shift the Pareto frontier? Because for ML practitioners, we aren't just looking for lower perplexity. We are evaluating models based on lower perplexity at a specific inference latency threshold.
The empirical results are incredibly strong. At the 1.5 billion parameter scale, the MIMO variant of Mamba-3 improves average downstream accuracy across a massive suite of zero-shot tasks by 1.8 percentage points over the next best linear model, which was gated DeltaNet.
That's significant.
And perhaps more surprisingly, it beats the transformer baseline by 2.2 points.
Which is remarkable considering transformers inherently possess exact recall capabilities via their KV cache, which is something linear models natively compress away.
Right. But the most important statistic for anyone looking to deploy these models locally or at scale is the efficiency trade-off. If you look at the Pareto frontier curves in the paper, Mamba-3, with a hidden state size of 64, matches the exact perplexity and downstream performance of Mamba-2 with a state size of 128.
And that is the crux of the innovation, because the decode runtime latency is directly governed by that state dimension.
Exactly. It delivers the exact same modeling performance with half the latency footprint. You can deploy a model that is twice as fast, or you can deploy a model at your current latency budget that is significantly more capable.
It's a win-win.
And it's not just basic next token prediction either. The paper demonstrates highly competitive real-world retrieval capabilities. And on synthetic needle-in-a-haystack tasks, its out-of-distribution length generalization is vastly improved compared to Mamba-2.
We do need to acknowledge the inherent physical limitations of the architecture, though. As a linear model with a fixed size compressed state, it fundamentally still struggles with information extraction from highly unstructured data compared to a transformer, which can simply attend back to the exact previous token in its cache. The fixed state size is a hard physical limit on pure unstructured recall.
So what does this all mean? Let's briefly recap the trifecta of innovations here. 1, we have exponential trapezoidal discretization giving us second-order mathematical precision, seamlessly generating implicit convolutions.
Right.
2, we have the brilliant mapping of a complex state space to a real valued matrix using the row P trick, unlocking TC0 state tracking dynamics like parity. And 3, the MIMO architecture, injecting ranked rally projections to saturate the arithmetic intensity of our tensor cores during inference without destroying training throughput.
It represents a complete ground-up reimagining of the linear mixer, driven purely by the realities of hardware execution and inference efficiency.
And the paper leaves us with a really provocative thought to mull over regarding the future of model architectures. They briefly explore hybrid models, because while Mamba-3 does face a ceiling with unstructured data retrieval, it heavily excels as a dense, logically expressive sequence mixer.
It really does.
The data shows that if you interleave Mamba-3 layers at a 5-to-1 ratio with no P, that is, no positional embedding self-attention layers, you completely mitigate that unstructured recall gap.
You basically combine the constant memory, continuous state tracking of the SSM with the exact match, uncompressed retrieval mechanism of attention.
It really makes you wonder, does the future of AGI reasoning belong not to pure linear models or pure transformers, but to chimeric architectures? Imagine a system where a highly expressive linear model like Mamba-3 handles all the localized, complex state tracking and logical synthesis, acting as the working memory, while the computationally expensive quadratic attention mechanism is relegated purely to a sparse, long-term memory retrieval function.
That's the billion-dollar question right there.
It's a fascinating paradigm shift for the industry to explore.